Okay, let's get started. Uh, so what we're going to do today is we're going to talk some more about linear models, how you create them and what they're good for and what they aren't good for. Um, and I wanted to start by reviewing some of the stuff we went over last week. So, uh, so previously, you have the text by kind, and I gave you a link to the Faraday book and some specific sections in that. Which I think are excellent. But for some of the nitty-gritties of how you use the LM function in R, I've found this site. He's a professor at Princeton, and he has some nice lectures on using R and LM to make linear models. So you might want to have a look at that if you want to have some more information. But briefly, if we have a data set, X, some data we've collected, and a response variable Y, we create a linear model. And that means we're going to see to what extent we can write Y as being some linear combination of X plus some constant term. Now this is the simplest model that one can create. And X can be either a single variable or it could be many variables, and then A is either a scalar number or it could be a matrix. But regardless, the same thing holds. We want to find the best model. I'm saying that showing that I have I may have issues with my transmission. If anyone's having issues hearing me, let me know. Okay, so X can be a single and many variables, and it's standard if there's more than one variable, the columns will be variables. Okay, good. And that the rows represent observations. And this representation is never exact, so we would write y equals ax plus b, or yi, the ith observation of y, is equal to a times the ith observation of x plus b plus some error term or noise. Okay, the epsilon is noise, and those are called the residuals. It's supposed to be noise. It may not be noise, but those are the residuals. And all these model estimates you have for the coefficients are dependent on hypotheses about the residuals, namely that the residuals are independent, identically distributed Gaussian noise. So what that means is that each of these residuals is a random variable. They're all normal with the same mean of 0 and identical variance. This hypothesis is essentially never exactly true, but even if the hypothesis on the residuals are not met, one can create the model. The problem will be that the estimates of how accurate the model are will be too optimistic, but more on that later. So just to write some notation, some math, uncorrelated means that if you look at these two residuals and think of them as random variables, their correlation is 0, and constant variance means exactly that the variance of these two random variables are the same for any two values. If you have more than one observation, more than one variable, it's standard to think of X as being n observations of P variables. And one collects this data into an n by P matrix called the design matrix. This matrix should be a full rank, and I wrote B greater than P, but that's a typo. That should be n greater than P. In other words, you need to have more observations than you have variables. If you have two observations of 100 variables, you can imagine that it's sort of intuitively clear that you couldn't create a good model. There's too many things, too many ways to fit it. But in modern data collection, where there's no shortage of data, it's essentially no longer an issue to have the number of observations smaller than the number of variables. Okay, as I said, in this case, OLS has a problem with a unique solution if you don't have that, but we don't see that much in real life. And you deal with categorical variables. It could be, color of eyes, height, sex, by creating dummy variables that take the values 0, 1. I'm going a little quick because this is stuff we talked about last week. Here's something I wanted to add, because you'll see this when you look in books. You'll see the design matrix X is written as a matrix X, X sub ij, where the I's, I'm sorry, this latex didn't come out properly for some reason. X is, X sub ij. X sub ij is the ith observation of the jth variable. And the beta are chosen so that if you let y hat be, so that's what the value you predict, the fitted value, if you will. The fitted value, see, you would sum from j equal 1 to p because you have p predictors. So the ith prediction would be the sum over all the j, which is all the different columns, the different variables you have, that, and you want to minimize that. And so this is a mathematical problem, and it can be solved regardless of how the statistics come and how accurate this model is. Okay, and one can use R to create this model. The LM function does that, and it gives you a lot of information. All right, this is all pretty much a review of what we did last week. Before I go into more detail, and we will, I just wanted to point out that you can always create a model, but that doesn't mean you've created a good model. So let me just get to the beginning here. Okay, so this is called Do Green Jelly Beans Cause Acne? And this is taken from a famous cartoon by XKCD. You'll see it in a second. So this is a short cautionary tale on hypothesis testing, and it's also an excuse to introduce you to some, pretty cool R code. And the operating principle is, if you torture the data enough, it will confess. And I wanted to get an exact attribute to that, but I've seen it attributed to Ronald Coase, who's a very famous statistician. I've also seen it attributed to a guy named Huff, who wrote a book on statistics. And so I don't know, but this is a valid statement. If you torture the data enough, it will confess. And that's the nature of hypothesis testing. It just provides evidence. So as I said, this is XKCD comic. And I think that if you appreciate this cartoon, it's better for you than if you read any full chapter on statistics. So here it is. And it says, jelly beans cause acne, scientists investigate. And they say, but we're busy playing Minecraft, but they do it anyway. And they say, we found no link between jelly beans and acne, p greater than 0.05. So in other words, they did a hypothesis test and it didn't come in with the p less than 0.05 that would make it significant. They said, that settles that. And then the other one says, I hear it's only a certain color that causes it. And the scientists are disappointed because they would prefer to play Minecraft, and they go and they investigate. We found no link between purple jelly beans and acne, p greater than 0.05. We found no link between brown jelly beans. Well, they all say that, except for over here, we found a link between green jelly beans and acne, p less than 0.05. Whoa. And it continues, and not accidentally, they go through 20 different colors. And the headline is, green jelly beans linked to acne. And the point is, it's supposed to be funny, because if you have random data, and you're looking at a 95% level of confidence interval, in other words, a significance level p less than 0.05, 1 in 20 times you're going to find it. So this is a nerd joke about statistics, and we're going to investigate that. So as it says, the point of the cartoon is that hypothesis testing, even under ideal circumstances, is very different from proof. This is what a hypothesis test does. This is what the output, these p-values and whatnot of your linear model tell you. It says, even under the best of circumstances, there is not enough evidence to reject the null hypothesis. And I put that in big, big bold, not enough evidence to reject the null hypothesis. Not that the evidence proves the null hypothesis. Now, you might remember when we were doing chi-squared, we went through the data on cancer and smoking. And we saw that the data showed that it didn't seem as if cigarette smokers had the same rate of cancer as non-smokers. It's important to point out that the study did not show that cigarette smoking caused cancer. It provided some evidence that the causal link that is so vital in these things was not given by that study. The study just suggested it. So in that case, there was evidence that there was enough evidence to reject the null hypothesis. Now, back to OLS, I just want to quickly show you. When you run a linear model, it gives you information about the coefficients. And it says this probability greater than t. When these numbers are very small, this is the probability of observing a coefficient that large under the hypothesis that the true coefficient is 0. So when you have these small p-values in the linear model, it says there's very small probability that the coefficient really is 0. Okay? And that's all the hypothesis testing is doing there. So when you get a small p-value, it doesn't prove that this is the correct numbers. It just says that there's a very small chance that the true number is 0. So back to green jelly beans. So let's create random data on jelly bean consumption and acne. The fact that this data isn't real, I think, makes the point even clearer. So what we're going to do is I want to create 20 colors of jelly beans corresponding to the first 20 letters. So if you will, A is azure jelly beans, B is beige, up through G is green. E would be ecru jelly beans. So we're going to create 200 random consumptions, people who consume jelly beans, and they consume only jelly beans of a specific color, and they consume one of 20 colors, and they consume some random number of jelly beans between 1 and 20, and they either do or don't have acne. That's the data set we're going to create. So I'm going to do some random things. So this is something really worth keeping in mind. When you're doing anything that's random, sample, a normal distribution, you should always use set.seed. Set.seed tells you random numbers. Computers can't just pick true random numbers. There's what's called pseudo-random numbers. They act as if they're random numbers. And basically, when you set the seed, it says start from this spot and now start creating the random numbers. Because it's only pseudo-random, every time you set the seed to that spot, it'll create the same set of random numbers. So in other words, if you use set.seed, you will every time get the same results. So if you want your data to be reproducible, you should always set seed. So I just randomly choose 1, 2, 3, 4, 5. So this means I could run this thing 100 times, and the first thing I'm doing is creating jelly bean count, and I'm sampling from the numbers from 1 to 20, 200 times, and so since there's more than that, I have to have replace equals true, which means to say I can sample I can have a given number occur more than once. But if I use set.seed 1, 2, 3, 4, 5, and this jelly bean count equals this, every time I run this code, I'm going to get the exact same 200 numbers from 1 to 20. All right. Quiz 1. Now, I'm going to ask you to respond via chat, and I'll keep track of it because when I give you the quizzes on the quiz format, you lose the screen, and what I discovered is that some of my answers are a little too long to fit on there in their quiz format, so you just answer via chat and I'll keep track of everything. All right, so we should always use set.seed 1, 2, 3, 4, 5. Choice 2 is always use set.seed to ensure reproducible. Choice 3 is always use set.seed so our ideas will germinate. And number 4 is it isn't important. So one of those choices, it looks like for now 2 is winning, which is good. We have 3-0 for choice 2, 4-0 for choice 2. Anyone else care to answer? All right, yeah, it's number 2. You should always use set.seed to ensure reproducibility. If you set .seed 1, 2, 3, 4, 5, that's fine, but there's no reason. You can even use set.seed equal to 1, set.seed 1, or whatever your favorite number is. But you should always use it, and that's that. All right, minimize that again. So we have the jelly bean counts, and let's create the colors. So there's this letters in R, and it just gives you all the letters. When I write letters with capital, it's going to give me capital letters. So I want letters sequenced from 1 to 20. That just means I'm going to create the first 20 letters. So this will be the letters A through whatever the 20th letter is. What is it? You're asking? All right, let's take a look. Letters, oops. T. All right. Okay. So I create the letters 1 through 20, and I repeat that 10 times. So I'm just going to have A through T 20 times. T would be the color turquoise. And acne, whether you have acne or not, I'm going to assume that it's a 50-50 proposition. As I say, I will assume that in our population, perhaps teenagers getting acne is 50-50. So if I create sample from 0, 1, 200 times, probability 0.5, 0.5, that means I'm giving a 0.5 probability to 0 and 0.5 to 1. That's going to be, and of course notice you have to put replace equals true. By the way, the default is replace equals false. So if you don't put replace equals true, this is going to throw an error because it say I can sample 200 times without replacement from only 2 things. So this is commonly known as a Bernoulli variable. And then I'm going to put all the data into a data frame. That's just useful. So I use the data frame command and I just tell it what the columns are. There's acne, which column, I'm going to take the acne variable and call it acne. I'm going to take the color variable and call it jelly bean color. And I'm going to take the count variable, how many jelly beans were eaten, and just call that count. And you have a look, you can see if I have this, my data set, I look at the head, which is the first 6 observations, only one person has acne of those 6. And they see what's a cyan, and they eat 16. They average eating 16 jelly beans. But notice number 2, it doesn't have acne, and they eat beige jelly beans. She eats 18 of them. So that person, it's not clear. And if I look at the summary, it's going to say acne runs between 0 and 1. Of course, it only runs 0 and 1. So the mean is 0.435. What does that mean? Well, the acne is either 0 or 1, so it means there were the number of ones so that it averages to 0.435. There were 200 observations, so we wound up with 87. So this tells me actually 87 of the people had acne. And the colors, you see it just describes that each of these colors occurs 10 times. And the count runs from 1 to 20. And the median is 12. So that means half the people ate 12 or less jelly beans, half the people ate 12 or more jelly beans. Okay, so that's actually useful. And what do we got? We should always plot our data. Now, we can use ggplot, which is, might as well because I'm going to do some more stuff with it. So I call library ggplot. You always have to load packages before you can run them. And remember, in the general ggplot, I put in the data I'm going to use. And since I'm always going to have XB count y equals acne, I can put that in this, which means anything I'm going to draw is going to have that. And then I'm just going to draw the points. Now, this is actually not very useful because every point is either 0 or 1. And adding color isn't going to help much, except you're going to see which points are that. But it's not very helpful. Agreed. So we're going to do a hypothesis testing. Do jelly beans cause acne? And that means we're going to create a linear model where y is acne and x is the count of jelly beans. Okay, so we want to create a model y acne equals some multiple times jelly bean consumption plus a constant term. And we're going to test the hypothesis that the coefficient of x, the count, is not 0. If that coefficient is non-zero, that means well, if the coefficient might and might not be non-zero, I don't want to prejudge it, but the hypothesis testing is going to tell us the probability that the x coefficient really is 0. The hypothesis is that the x coefficient is 0. So a small p-value is going to indicate that it's false that the true coefficient is 0. So p less than 0.05 is what we're looking for. That'll mean that there's a small probability that you'd get that coefficient if the real coefficient was 0. So if there's a p-value of less than 0.05, that means that we've provided evidence that jelly beans cause acne. That, the true coefficient of x is unlikely to be 0. If the p-value is greater than 0.5, we're going to reject the hypothesis we're going to accept the hypothesis that the true coefficient of x is 0, which would mean that there's no causal relationship between jelly beans and acne. Drum rolls, please. Okay, so this is what I just said, but maybe let's just repeat it one more time. The p-value that the summary function is going for the linear model is going to show is going to be the probability of observing a coefficient that large if the true value is 0. That's the hypothesis. So the hypothesis is the true value is 0. So if the p-value is less than 0.5, we can make the statement there is less than a 5% chance we would observe a value for the coefficient this large or larger under the hypothesis that the true coefficient is 0. So if the p-value is less than 0.05, we accept that the coefficient is non-zero and we put it in the model. We use the actual value we calculate. That's our best guess as to what the real value is. But if the p-value is greater than 0.05, we're going to accept the hypothesis that the true value is 0 and not leave it in the model. So in other words, when we do this model, if we get a p-value less than 0.05, that's providing evidence for the hypothesis that jelly beans cause acne. And just once again, accepting the null hypothesis, the true coefficient of 0, means that there is the value of 0 is in the 95% confidence interval for the true value of the coefficient. Okay, so if we accept the null hypothesis of 0, we win. What happens? Now, okay, so I said 0 is in the 95% confidence interval for the true coefficient. This means that if you perform this experiment 20 times, 5% is 1 out of 20. So on average, 1 of the 20 times, you will reject the null hypothesis that the coefficient is 0, even though it's true. 5% of the time, you will observe effect this large by chance. That's what a 95% confidence interval means. And I feel so strongly about this that people should really pay attention to this, that this slide just repeats what I said yet another time. There's a 95% chance of something being true, means that if you test it 20 times, you're going to get a false result. Okay? So in the jelly bean issue, if we're using a 95% confidence interval, this means that in 1 in 20 tests on average, we're going to get a p-value of 0.05. We're going to accept the hypothesis that jelly beans cause acne, even though there is no causal connection, as a cartoon. So I want to summarize how you should think about p-values from another infographic from XKCD. So here's the values. If it's 0.03, it's highly significant. 0.04 to 0.49, it's significant. If it's exactly 0.05, oh crap, redo calculations. If you get p-values close to it, on the edge of significance. If they're higher than that, highly suggestive, significant at a p less than 0.10% level. And if it's greater than 0.1, let's look at this interesting subgroup, which is exactly what happened in the jelly bean thing. They looked at the interesting subgroups and they found that green jelly beans caused cancer. So there you go. Quiz on hypothesis testing. Which of the following is true? Hypothesis testing will allow one to determine the truth or falsity of a hypothesis. Hypothesis testing will allow one to determine the truth or falsity of a hypothesis 95% of the time. Hypothesis testing will allow one to be 95% sure of the hypothesis. Or hypothesis testing will provide evidence for the truth or falsity of a hypothesis, but will not provide a causal explanation. I'll wait your answer. So I have 1 for 4. Spoiler alert, I hope no one is thinking of answering anything but 4. Okay, great. Everyone's saying 4, so, which of course is correct. Hypothesis testing, the point is, does not provide any causal relationship. It provides evidence for or against a hypothesis. Drum roll, and let's do the model. So we have this data, and we want to see how acne relates to the jelly bean count, how many jelly beans you eat. Okay, and we create this model, LM, and I'm just a simple model. I'm going to model acne to jelly bean count, and the summary gives me the information. It tells me the formula, tells me the residuals, so I'm never more than a half off one way or the other or so. It gives me coefficients. Now, this is worth looking at. It says the intercept is 0.55, and the jelly bean count is very small. Now, it says it's very sure that this intercept is statistically significant, which is so much as to say that it's very, very sure that the true mean of acne is not 0. And notice it says 0.55, which is very close to the 0.5 that you would expect. And in fact, it's 0.47, I think we saw in this sample. So this is very reasonable. And notice it says that the actual coefficient it expects for the jelly bean count to be very small. So even if you accept this hypothesis that how many jelly beans you eat affects acne, it's not a very significant effect. It gives you an estimate of 0.01, and notice it calculates a t-value that isn't so large. It says that there's an 8% chance of getting a value this large if the true coefficient is 0. But 0.08 is bigger than 0.05, so we're going to accept the hypothesis that this true value of this variable is 0. 0 is in the 95% confidence interval for the estimate, because the standard error is about 0.06, and 2 standard deviations of 0.06 will take this up to 0. So 0 is in the 95% confidence interval. We accept the hypothesis, and we say jelly beans do not cause acne. All right, and I think that this is just what I said, namely that acne is either 0 or 1 with a ratio of 50-50. So the equation was kind of what you'd expect, and we reject the hypothesis. We accept the hypothesis that the true coefficient of jelly bean count is 0, because we have a p-value of 0.08, which is greater than 0.05. So the 5% level of significance, we can reject the hypothesis. Well, we accept the hypothesis that the coefficient is 0. All right, so here's the next quiz. The p-value for the coefficient JB count is 0.08. This means there's an 8% chance jelly beans will cause cancer. There's a chance 2 is there's a 92% chance that jelly beans, not cancer, acne, cause acne. And number 3, there is an 8% chance of observing a coefficient that large or larger if the coefficient is really true. And I invite your responses. I have 3. I have 3. And I have 3. Yeah, this is the probability of observing a coefficient this large. So there's an 8% chance, which is greater than the 5% cutoff, so we accept the hypothesis. But and everyone agrees that it is 3. All right, good. So let's torture the data a bit. We kept track of jelly beans by color. So maybe, as the cartoon suggests, acne is only related to eating a specific color of jelly bean. Now we can run a test on every color of jelly bean, and if we get it, we will get a significant p-value for some color. Okay, so how to do that? Well, we want to calculate p-values for every for the linear model for each particular color. So I'm going to get, there's 20 colors, so I'm going to have 20 different p-values. So I first create the matrix to instantiate, if you're a computer science person, the p-value matrix that I'm going to put the data in. And R aside, when you're putting data into something with a for and X loop, you always want to create the data container outside the loop. Now, something like this is completely irrelevant in terms of time, but when you have really large data sets, the way R runs things and manages memory, if it has someplace already to put the data in, and you just say put it in this spot, it's very quick. If you're adding on, like if you use like a C bind or an R bind command, every time it has to recreate the matrix and put everything in its right place, and it's much more time consuming. I mean, for 20 observations of this, you're talking about, maybe nanoseconds, so it's irrelevant, but for large calculations, always good, create the data first. So what I'm going to do, for I equal 1 to 20, I have 20 different color jelly beans. My index is going to be which jelly bean color is equal to the ith letter. So for example, when I equals 1, the letters of 1 is A. It's going to give me an index of which of JB colors. Remember, the JB color is a 200, a vector of length 200, and it contains each of the colors 10 times. So this is going to give me the index of which of those 10 spots the color is the letter A, respectively. And then if I say acne of that index, it's going to give me the corresponding conditions for acne. Okay? So, and temp count, if I go JB count and I just call it on the index, it's going to give me the counts of how many jelly beans. So for example, when I equals 1, as I said, there's going to be all the people who ate jelly beans with color A, for apples, say, and then we're going to see how many jelly beans they ate, and we can make a model for only the people who ate jelly beans of that color. Okay, and by just this, and then the p-value of I, if I look at this, remember, well, the summary of the model, that's an object, and it has, various pieces of data, and one of them is coefficient. And it turns out that the coefficient in spot 2, 4, coefficient is a 2x4 matrix. That's the p-value. Now, you can discover this in many ways. Let me just point out. If you look at the coefficients, you have 2 columns, and the 4th column, you have estimate, standard error, t-value, and probability greater than t. That's the p-value. So the second row, 4th column, is where the p-value for the count term is stored. So that's where that comes from. So this is going to give me the p-value for the ith jelly bean. And so now I'm going to have this, when I run this code, I will get 20 different p-values, and I see the minimum p-value is 0.01. So that would say that for whatever value that is, the p-value is 0.01, that's under the 5%, so for that particular color, well, it turns out it's using the which.min will say what's the value, so it's the 15th element of the 20 valued matrix, and letters of 15, which I just write programmatically this way, is O. So in fact, green jelly beans don't seem to cause cancer. Orange jelly beans cause cancer. And so why do I say that? Because when we ran the linear model for just the jelly beans that were orange, we got a p-value of 0.01. So we have to reject the hypothesis that the true value of the coefficient is 0, and accept the hypothesis that the hypothesis that the true value of the coefficient for acne, for jelly bean count in relation to acne for orange jelly beans, is non-zero. So there we have it. So what have we shown, and what have we learned by this, besides the fact that, well, this might be, maybe you could summarize it by one of 2 statements: statistics don't lie, statisticians do, or Disraeli's famous comment, there are lies, damned lies, and statistics. So what we learned is the data could be tortured to confess. But what have we really shown, and since we're dealing with probability, what we've shown really is the true statement that if we do enough tests, some of them are going to go good, because the correct statement is at a 5% level of significance, we cannot rule out the possibility that orange jelly beans cause cancer. One needs to do further testing to confirm if this hypothesis is actually causal or not. And needless to say, you won't find that. Now, incidentally, I didn't want to, get people nervous, but I could have done, control, copy, replace, and replace every instance of acne with cancer. And then one would be discovering that orange jelly beans cause cancer. And, so the point is all these tests do is provide some statistical evidence for what we want to see. They don't provide a causal effect. Now, there's many situations in which that's really enough. But, I don't want to get too deeply into it. It's really something, called Bayesian statistics. But something, that we really consider in real life that's important is how realistic our hypothesis is. Given, that something's just completely random, you really need a lot more evidence than is something that makes sense. For example, if you were going to test the hypothesis that when Intel has good earnings, so does, some maker of computers, that's, if you found this kind of statistical evidence, you'd be willing to believe it. It's because it's a priori plausible. And this is, I don't want to maybe think of this as an advertisement for some further class in the program, where, because certainly when you do machine learning and we're more interested in prediction, understanding our hypotheses and what they mean becomes much, much more important. But the moral of this story is that we have not shown that orange jelly beans cause acne. And of course, as the data is random and just completely randomly aside, we knew that. Okay, I also wanted to, bring this conversation home in the context of counts and the Fisher exact test. So we had count data on the acne, yes or no. We could have done a Fisher test or a chi-squared test too. What you would have had to do is, from the counts of jelly beans, use a cutoff for jelly bean eater and, sort of decide arbitrarily whether or not, what was the level which you want to call somebody a jelly bean, whether it be 12 because that was the median value. So somebody who ate 12 or more jelly beans was a jelly bean eater. Somebody who ate less than 12 was not. Whether you wanted to use 10, that's so more like the half. Whether you wanted to use 5, all these things, would be issues that in the real world, in the real statistic test, you would have to think about. Now, a 2x2 table has 2 rows and 2 columns. So how many degrees of freedom that it has? Remember, the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So it would have 1 degree of freedom if you were doing this. So you would want to use a Fisher exact test, not chi-squared. And as it says here, I want to give you an example to show that hypothesis testing for counts can be just as problematical. So, and I also want to use this as an excuse to show you how to do something that's really useful and important to do with our coding. So I'm going to be doing some sampling, random sampling, so I set the seed for reproducibility, and I create 2 matrices of size 100 by 2, and I'm going to initially populate them by with zeros, and I'm going to call them heads and tails. So what are these 2 matrices going to do? This first matrix is going to contain 100 observations of flipping a fair coin 100 times and observing how many heads and tails you're going to get. And the 55 is going to do the same thing, but from one where I believe the probability of getting a heads is 0.55. Let's see. So sample 1 is 100 draws from a 50-50 coin, and sample 2 is 100 draws from a 55-45 coin. So what does this code do? I run from I equal 1 to 100, and each time I sample from 0, 1 100 times, so that's sample from a fair coin 100 times, and sample 2 I sample 0, 1 100 times, but I give it the probability of a heads is 0.455, and the probability of a coin is 0.45. So in the end, and then I just say the sum is of the sample is going to be, that's going to be how many ones you had, that's going to be how many tails. So I'm going to put that in the second column, and for every I I'm going to do this, and then I'm just going to say even is the number of heads is 100 minus the number of tails, because each time was a flip of 100 coins. And let's just take a look. It looks about right. I get the mean of the heads of the tails is 50, and for the fair coin, and the mean of the tails for 50 is 45, which is just what we'd expect. So you can see I flipped 100 coins. First time I got 48 and 52 on the fair coin. I got 43 and 57 on the unfair coin. The second time I flipped it 100 times, I got 45 heads and 55 tails in the fair coin. Notice, by the way, that it's very rare to get a 50-50. Okay, but I do have these 100 things. So I have 100 times I can test. So I can make a Fisher test for this. Would be a 2x2 table. It would be 48-52, and the 43-57 would be underneath. This would be another 2x2 table of, and we'd want to see if this 45-55 was likely to be drawn from the same. And then the second time we did a 46-54, is it likely that they were drawn from populations with the same mean? So again, I instantiate a matrix to contain these 100 answers, and I give the Fisher test to I bind by rows. That's what I said, and then I just want the p-value, and I put that. So when I do this, when I run this code, I'm going to get 100 p-values. And what do I get? Notice I get answers all over the place. I get answers from 1 to 0.002. So we know, in fact, that all 100 samples were drawn from the same things. In fact, they're not fair, and we get answers all over the place. And in fact, we know in reality it should fail. Not that it should fail or pass the Fisher test, but we know, in fact, that the tables were drawn from from populations with different means, right? And so you get an idea that, by the way, the mean value is 0.48, so which is significantly larger than 0.05. So almost all the time, excuse me, almost all the time, I don't know why this is doing this. So almost all the time, you would accept the hypothesis that the two samples were drawn from the same population, even though it's false. But you might want to ask, how many times did the test correctly detect that the samples are different? You could just sort of look over the list of all 100 things and count. You're looking for all the times that it's less than 0.05, but there is a better way. And that is, we can use which function and the length function to do this. So you've seen me use this a couple of times, but I want to, flesh this out, because it's something that you should know how to do, and you will have to do both in your upcoming assignment and in real life, when you want to sort of say, how many times did we actually have something happen? So let's remember that in R, if you put two equal signs, you're asking, are these two objects the same? So A equals B means A and B are the same. And if you do that in R, you're going to return a logical. A equals B with one equal sign means assign to A whatever's the value in B. Okay, and it always will assign to A what's in B. So for example, if I say A equals 7, B equals 5, and I write A equals B, I get false, because it's 7 doesn't equal 5. If I say A equals B, I've now assigned to A whatever was in B. So in fact, A is no longer going to be 7, it's going to be 5. Now if I say A equals B, I get true, and because A has now taken the value 5. So this is something that comes up constantly when you're actually writing code, and it's worth knowing how to use it. So to just go on, if instead of 2 equals I use exclamation point equal, that means not equal. And if you want to say and for 2 conditions, it's the ampersand, that, and the or is a single straight line dash. So you can use these in combination to get an index with the which function to get an index of which elements satisfy some condition. The length of this index is how many, okay? And if you apply the index to the vector, you're just going to get the elements satisfying this condition, okay? This is interesting. Yeah. So somehow I've lost the slide in which I told you what vec2 is, but vec2 is just a vector of length 10 containing the first 10 letters. So in fact, let me just show you how you create it. Maybe I have it here. Okay, so maybe let me make this a bit larger so you can read it. Okay, so vec1 is I just take all the numbers from 1 to 10, and vec2 is the first 10 letters, which is A through J. I wrote 11, but that's not right, it's 10. So if I write, if I write which vec1 greater than 8, that'll give me the indices of it'll give me the indices in vec1 of the numbers that are greater than 8. That's 9 and 10. If I look at the length of which vec8, it'll tell me how many. And if I create a new vector with just these, it'll give me all the numbers greater than 8. So let's just see this in action. I don't know why it's not doing this. Well, let me just cut and paste this. Maybe that'll work. It should, okay, so you can see which vec1 greater than 8, it gives me 9 and 10, because in spots 9 and 10 are the numbers 9 and 10. If I ask for the length of which vec1 greater than 8, it gives me 2. And if I create a new a vec1 of which vec1 is greater than 8, it gives me just the vector of the numbers that are greater than 8, which is the vectors 9 and 10. So, yeah. All right, and so in the second case, I'm just I've created vec2, which is all the letters from 1 to 10. Which vec2 is greater than h? H is the 8th letter, it'll give me 9 and 10. Which vec2 is less than b? It'll give me the index 1, because only the letter A is less than b. And a more complicated one, which vec2 is greater than d, and vec2 is less than or equal to h? This will give me all the letters that are bigger than d and are less than or equal to h. You see less than and equal, not less than. And those are E, F, G, H, which are in positions 5, 6, 7, 8. And you can see which vectors are greater than h, it gives me I and j. Which vectors are less than if I take vec2 of which vectors in vec2 are less than b, it gives me a. And if I get take vec2 and I call the index which vectors in vec2 are greater than d and less than h, it gives me EFG, which is, since d goes there and h goes there, it does that. So this kind of indexing is something you see me do, and it's really, really useful, and I wanted to specifically point it out to you as a method. So if I go to odds, I can say fail is which odds less than 0.05. These are the remember, odds was the odds of these two samples of coin flips being the same. So this will give me an index of which times when I did the sampling I got a p-value of less than 0.05, and those are the ones for which you would find that there's the probability is less than 0.5% that the two sets of coin flips came from its populations with the same mean, and that you would correctly see that the two coin flips, the two sets of coins were differently. One had 50-50 heads, one had 55-45. Now, so a fail is an index, and the length of fail tells me how many times. There fail 5 times. I took 100 tests, and 5 times it failed. 5% of, in fact, this time it works out perfectly, that 5% of the time the hypothesis test failed. And then I just wrote summary. You can see when I take odds and I call the index fail, it's just going to be the cases where you had a p-value of 0.5 or less. And you can see mostly they were pretty large. The smallest one was really, really teeny. The median said, you know, there was 5 of them, says 2 of them were bigger than 0.46. But this is just, so that's the point. All right, so what have we done? We've talked about confidence intervals and what they do say and what they don't say. And what I hope I've convinced you is that when you do these things, they're not like, you know, the 10 commandments come down from the temple. They're not, you know, laws that are written in fact. They're just evidence. And so the next time you see on TV or read a scientific study has just shown something, you'll hopefully after this say, well, it probably hasn't shown something. It's probably provided evidence, but I definitely want to see it done again before I believe this. So the next time you hear chocolate causes cancer or chocolate prevents cancer, just keep this in mind. And one final takeaway, it's Ronald Fisher, who invented a lot of this stuff, came up with the idea of 95% confidence intervals. 95% is in some sense an arbitrary number. In practice, when one really needs to be sure, one looks at 99% confidence intervals. But there's no reason not to consider 98% confidence intervals, 80% confidence intervals, and most importantly, they are confidence intervals and not divine truth. All right, so green jelly beans and orange jelly beans, we have no evidence about whether or not they cause cancer. All right, having said that, let's take a look at what the data, you know, what some linear models do. So I'm going to go back to the famous iris data set, which I believe was used by Ronald Fisher. So I load the data set iris with data iris, and I take a look summary. So we have, what does it have? It tells me that I have 5 variables: sepal length, sepal width, petal width, and species. I have 50 setosa, 50 versicolor, and 50 virginica. So there's 1, 2, 3, 4 numerical variables and 1 categorical variable that takes 3 values. So if we use this in the model, it's going to create 2 dummy variables, and you'll have an intercept. So let's just do a simple model. Let's see, can we predict, does petal width, can it be predicted by sepal length? So I just do a simple model, linear model, petal width, you know, the tilde is sepal length, and my data is iris. And I call that model, and I look at the summary, and it gives me this information. And let's take a look. Well, the first thing to do is look at the p-values. They're both incredibly small. So you reject the hypothesis that the true coefficients of the interceptor sepal length is 0. In this case, you know, these numbers are so small, regardless of whether any hypothesis there might be on the residuals, it's likely, not surprisingly, that sepal length does it has some influence on petal width, and in addition, there's some sort of mean value. Okay, and what else do we get here? These are the residuals, which we'll talk more about later. We get a multiple r squared of 0.67. And notice the r squared and adjusted r squared are very similar. There's only two variables. They should be essentially identical. And the F statistic in this case tells us even less than these p-values. The F statistic would be the probability that there was nothing in the model. There were no coefficients. This is just writing out what I said. The F statistic is the calculated probability that all coefficients are 0. R squared is the percentage of variance explained by the model. One should have a look at the data always, and you can do this by taking a plot. And I think once you get into this stuff, ggplot is much easier. So I load ggplot, and I tell ggplot that my data is iris, and I'm going to use x to be the sepal width and y to be petal width. I want to predict petal width from sepal length. And then I say, in addition, I want to get the least squares line, print it. And then I want to, just see where the actual data points is. And we do this, and this is the model we got. And we can see that this is clearly true, but the way this is sort of in two blobs, and we know there's three kinds of things, it does suggest that this plot suggests in a way that just looking at the data of the linear model, just looking at this wouldn't, that probably you want to consider things by species. Now, just to get an idea of that, if I do ggplot iris and I give it the same information for aesthetics, but I add fill equals species, what it's going to do is it's going to keep track of everything by species. And now look, here we have the three species. My computer is acting a little funny with respect to I apologize. I don't know what's going on. My computer. Okay, that's what I wanted to do. You can see that if you go by species, it's really pretty good, but there's just a difference in the relationship per species. So we saw this a bit with something else last week, but you can see that when you do it this way, you're getting something, and the reason why you have this blob of data down here is Setosa just has a very different relationship. You'll notice that it's a much flatter relationship than for the other two species. So that was useful. Now, let's just take a look. If I want to do it without an intercept, I just want to say is petal width related to sepal length. Remember to do that, I just add +0, tells it don't give it an intercept. Now, when I have the coefficients, there is no more intercept, there's just sepal length, and it's still very significant. And the r squared, it was 0.67, it's now 0.80. And let's go to the next thing. So why did the r squared go up with one less variable? R squared is the percentage of variance explained. When you add more variables, you can always explain more of the variance because you can always set the coefficient of the new variable to 0 and get the old model as a subset. So when you add more variables, r squared goes up. And yet here it is, we remove a variable and it goes up. That shouldn't be. What's going on? Okay, so this is an important little thing you need to know about. Usually the variance is related to how much the data differs from the mean. If you throw out the mean, it has to use a different formula. So it's always true r squared will go up when you add more variables, r squared will go down if you take away variables, except when you get rid of the intercept. And the reason is because when you tell it no intercept, the linear model function uses a different formula. So it's calculating something different. I don't want to, drive everyone nuts with after an hour of this with formulas, but if you go to this page, you'll see a full explanation with the formulas, and in particular, you'll see what the modified formula is. So this is a very important little caveat about doing linear models. When you force the intercept to be 0, you can no longer compare to R squared. Okay? So, and then I'm just saying this again. R squared goes up with more variables. Now, equally importantly, you don't want to just add more variables to a model just to get R squared. That it'll go up is absolutely a fact. But there's this principle called Occam's razor, sometimes it's called the principle of parsimony, which says the simplest model that explains the data is the best. And Albert Einstein said it, we want a model as simple as possible, but no simpler. And the reason for that is twofold. Okay, the first is if you want to use your model for prediction, as you add more variables, the predictive power goes down. So that's the main reason. And the point is when you add more models, you wind up modeling the noise in your data. Unless your model is perfect, there's noise, and all you're doing when you're adding more variables is really it's just modeling the noise. The new variables will just be used not to really understand any kind of causal relationship, but it'll just try and model the noise. And also, as I said, as more variables are added, more data is needed to keep the same level of certainty about the prediction. So this is something the linear model, and the outputs from it doesn't show, but if you're interested in prediction, as you add more variables, if you want your predictive accuracy to stay high, you have to have many more examples, and it goes up typically doubly exponentially. So it's a serious issue. So you want to, if possible, use less variables. All right, I promised that I would discuss ANOVA, and so I want to briefly talk about that. ANOVA stands for analysis of variance. It's a thing in and itself, but in relation to regression, ANOVA will tell you whether adding more variables to your model is going to add statistical value. So it adds variables one at a time to your model in the order that you've given them, and tests if they are statistically significant. And as I said, variables are added to the ANOVA analysis in the order of the formula. So here's an example. If we just if we look at the iris and we predict petal width on all the variables, now we're going to have more than one. And if I look at summary, we see we have an intercept, we have the two dummy variables, and we have the 1, 2, 3 numerical variables. So you have 5 variables and an intercept is 6. And notice that R claims that they're all non-zero, they're statistical tests, though if the residuals are not normally distributed, this one would be the first most likely to go out. But in any event, if I just call the ANOVA function, it'll give me the same things. It'll just tell me that I should keep adding, all these variables should be kept. Now, the jitter function is just a function that adds a little noise to your data. So I'm going to create a new data set called iris2. I'm going to add to iris, I'm just going to take the iris sepal length and add some noise to that and add that as a new variable. So notice this new data set has all the variables of iris and then the same variable repeated. Now if I run a model on petal width on this data with the extra unnecessary variable, we will see that it decides sepal length, it decides that sepal length and jitter are unnecessary now. Notice that what has happened is because these duplicate each other, rather than deciding to throw one out, it says these both don't belong in there. If I do analysis of variance, it correctly says leave in sepal width, but now when you get to jitter, this duplicate of sepal length with noise, you can throw that out. So in this case, the ANOVA shows something more accurate. So there is a reason to use ANOVA at times. when you're actually doing these models, it always pays to look at plots. I mean, pictures will tell you things that other things don't see. So if I just plot the linear model, here I want to plot petal width against petal length, we see that the linear model is pretty good, but we see the same sort of thing where we see it appears like there's two different, arguably distinctly two different kinds of data, and maybe you see a separation here. And of course, since we know that there's this categorical variable, we should look at that too. So now if I do the same data, I say iris, I want the aesthetics to be the same as before, but again I say fill equals species, which basically means create a different color in a different chart for every different species. Now we see it. And we see, incidentally, what we see is that for Setosa and Versicolor, and particularly Versicolor, the model's pretty good, but for Virginica, it really seems to be not such a great model. And this is something that you wouldn't pick up from just looking at any of this. I mean, it just says all the coefficients are, of the different the categorical variables are significant. So looking at data is useful. And with that regard, R has a plot function for linear models. So remember, model 2 was just this was the model with the iris data. And if you tell R to plot your model object, it's going to give you 4 charts. Now, in fact, when you do it on the screen, oops. This is what's going to happen. It's going to say, hit return or enter, and it's just going to show them to you like that. And so, and of course, if you're in RStudio, it's not so bad because all the models are saved, but you can't see them all at once. And we see we get this incredibly long thing. However, there's a nice function, par for parameters, and you say par mfro equals c of 2, it says take the 4 plots and print them all together, 2 rows and 2 columns, and it works for anything. And then if we do that, we get all 4 nicely like that. There's a very old saying that when you're a hammer, every problem looks like a nail. And back in the days when linear models was the only game in town, doing incredibly detailed analysis of your linear model to determine how you can make it better was important, and using all these charts was important. They're less important now because nowadays we have, with fast computers, we have much, when data is not really suitable for linear modeling, we have all sorts of other techniques. But you do get these 4 plots, and let me just describe them. So the residual versus fitted is exactly what it says. It tells you how much residual value you have versus where you fit it, and you want this to be random. That says that the residuals have nothing to do with where you are. If this sort of fits some sort of function that looks like something that's a real function, that says the residuals still have some data in them you missed. Okay, remember the residuals are supposed to be normally distributed. A normal QQ plot of the residuals versus the actual values will tell you to what extent this is true. If the error terms were normally distributed, they would all lie on this dotted line. That's what a QQ plot does, is it plots how many you have observations in a given, in the theoretical quantile given by a normal distribution versus what you're seeing. Now this is absolutely typical of what you see almost all the time with data that's not normally distributed, which is that you get most of the stuff fits very well, but what this is saying is that there's way more there's way more residuals that are very large negative or very large positive. This is what's called fat tails. And in any data involving human behavior, I claim you're going to always observe this, because human behavior is never normally distributed. We exaggerate the extremes of behavior. And let me talk a little bit about these other two words. So normal QQ is what I said, and this is just repeating it. And as for the last two, scale location compares the fitted values to the scaled residuals, and you want the residuals. Part of the hypothesis is that for linear model estimates to be accurate is you want the residuals to have equal variance. And that would mean that there's no connection between the fitted values and the scaled residues. And the closer that red line is to horizontal line, the closer that is to true. Let me just show you. So this is showing that there's some variance in the residuals, not a huge amount. And residues versus leverage, that's a little bit hard to explain, but the main thing is this dotted line is Cook's distance. If you have observations that lie outside there, so if I had some observation down here or sort of down there, those would be Cook's distance is a measure, a notion of sort of how important a particular observation is. So if you have observations down here, those are observations that are having very large influence on your data. Now, that means they're outliers. Now, outliers does not necessarily mean bad data. Outliers need to be examined to determine if this is due to some measurement issue or if occasionally your model is just going to be really, really bad. For example, if you were to do this sort of thing, create a linear model for returns of stock prices, you would definitely find there were a few observations that were influenced. You would find that there were a few times outsized return, most of them to the downside, negative returns. In this case, it's not bad data. It's just an observation of the fact that linear models can't work very well in that context, because essentially always there's far more large negative returns that any kind of linear model could hope to predict. So in the case of financial data, you're going to see outliers, but they're not bad data. They're just evidence of the fact that a linear model cannot capture all of what's going on in the stock market. All right, so that's it. I think at this point you guys have a pretty fair handle, or I've given you the opportunity to have a pretty fair handle on what to do with linear models. I've created a midterm project that'll involve doing some things related to this, and I will see you next week when we move on. We're going to talk about ggplot and using it to ggplot and dplyr, and using that to help in a data analysis, and maybe a few other things. All right, that's all I have to say for today. Are there any questions? Anybody have any questions or comments? Let me see if I have to push this up here for me to be able to see it. All right, in that case, I will bid you all to have a good rest of your day. Assignment is tough, as somebody wrote. Hopefully that today's lecture helped. I did make it a point to cover one or two things that'll be there. The assignment is tough, that's fine. If you have questions, feel free to email me, or I know there'll be TA sessions, but I absolutely don't mind if you send, if you need an answer. I'm generally pretty good about answering email. If you send me an email and say I don't understand this, I'll be glad to post more information. I mean, it definitely is the case. There are sometimes things I think I've explained well, and in hindsight I didn't explain well, and I'm happy to take the opportunity of a question to have another go at it. So the assignment is tough. If you have questions, feel free to ask them, and say, I'm having trouble with this. Can you give me some more information about this? Where can I find out more about this? All right. Anything else? All right, I'm going to end this session then. I did remember to record